Welcome to a new test and teardown video. This time it's an RFM100. It's actually a Rohde schwarz product, as far as I know. It's just don't say Rohde schwarz on this unit as well. I can't find it, but definitely is a Rohde schwarz. I think it was from 1989. And there is a battery in here. Bat check. I heard there was no batteries in this one. And I heard there is a mysterious error in this one. So I'll see if I can figure that out. Meanwhile, we're going to see how this was designed. So it's a SVR meter, or a forward reflected meter, where we can measure RF power from a transmitter to an antenna. So there's a feed-through coupler, actually two. So this is the frequency range 25 to 200 megahertz on this connector. But if your frequency is more than 200, then you need to go to that one. So from 200 to 1000, and then obviously you need to select the correct input system to your readout unit. And then there is a heat sink, and that will be the outputs. But there's also a dummy load here in the middle, and that should be able to handle 30 watts. And that is the nice diagram to show the forward and reflected and the SWR value. Let me do like this so you can have a good look on that. But it's super easy to calculate. All you have to do is this, la 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 la, instead of just looking it up in the table. So we got, what, 8 cells in here to change battery, remove rear panel. Alright, so that'll be those screws. But first, shouldn't it be able to measure a little bit of power without batteries? I don't think so. Oh yeah, there is another really cool feature about this. Nice little handle. Ta-da! What do you think about that one? That is so nice. I love it. And then this whole coupler unit, you can unscrew it here from the side. So if you want to have a really neat permanent installation in your lab, you can take the power detector bridge here and put this somewhere behind your radios where you don't have any extra long leads, and then there'll probably be some DC signals for the meters, right? I mean, there's not a lot of weight on this unit. So positive battery, negative battery. Aha, now it makes sense. So in the battery test, you hold this in for battery check, and then it's turning on, and then it will stay on for 5 minutes. There is no off. And then it will measure the battery in the negative and the positive half of the battery. So it's a positive negative battery system. All right. So the meter seems to be able to move real good. Even it was dropped. And that is, of course, easy to repair. But first, we need to have function back in this thing. So that is 1 watt of forward, and then 1 watt of reflected. Okay. So it can go all the way to 100 forward or reflected. So it doesn't really matter what is what in the coupler. So it's a completely symmetric coupler. So I don't know what is most fun, to look inside the couplers or to look inside the battery compartment. Let's have a look. What are we gonna do? Yeah, okay, so that was real easy, just to unscrew and take out the back panel. They could have made a little finger thingy here so you could peel off the replay. There is no such thing, but if you know the trick, stick in the finger here and then push up. Then you can take out the plate. And what I see here is something that always makes me a little bit sad. Look at that, we got some leaked cells. So somebody forgot to remove. Oh no, bad boy. Always remember to remove the cells from equipment you don't plan to use in the next real near future, because I actually see this as a killing factor in a lot of equipment that I got. People always think that, yeah, I'm gonna use this next week. It even says here, best before 2029. So I mean, those are not old. They're just leaked. Why are they? Maybe this unit drains the cells. I will just take them all out and measure the voltage. I mean, so far only one leaked, right? Well. All cells contains or deliver 1.5 volts. So I can't explain the leaky corrosion stuff on one of them. So there's actually a little funny thing here when I look at the, let me see if I can get this to. So we got 3 wires, so that is a positive and a negative supply, and all of them, as you can see with the tiny little wire down there, they go in series. So far so good. This one is the most negative, that is the brown one, and the most positive is the orange one, right? Okay, so that's how it is. But the center is a red one. But that is not the center. The center is up here, right? What? Is this correct, or it's not symmetric? Can you see what I'm seeing here? So you understand my frustration. Is this really correct? Is the fault really that simple? Is it supposed to be like that? I can't find schematics. That is also a problem. So how do we get this out of the case? Those 4 screws, and then let's just keep this side on, and also some more screws here on the top. I mean, yeah, let's try and do that. Yeah, but that was the first little thingy I'm a little bit worried about. So now it's out of the case. We can inspect a little bit deeper what this is all about. So only 3 wires from the sensor unit, and they're really well filtered. 3 capacitors to chassis, 3 inductors, and then 3 feed through capacitors. And then we go down here, 3 inductors, and they go to the PCB. Oh, look at that. They didn't even bother to solder all the solder points on the switch. I mean, I don't know. So then there is a double-sided PCB with 2 op amps, and they are of course doing exactly the same, the forward and the reflected. And that is kind of all there is to it, really. So how is this power on and the 5-minute works. I don't know exactly how that works because I don't see anything at all. Maybe you need to hold this in for it to be on. Oh, see, there is no clickety click here. So, but where is the automatic hold it on kind of system here? Because I don't see it. Maybe there's more. Yeah, there's more. There's a PCB here at the back as well with some flat cable, and that flat cable goes to, where's that going? Yeah. Ooh, this can't be good. So we got some black corrosion here, and somebody did indeed solder on that wire. So is this wire going? Nobody's been soldering on the top ones, so I just gotta take this as a correct way. Meanwhile, I actually already think I found the bug. I don't know, did you see this? That one is not connected. See if I move this. It's not connected. That one fell off. That PCB here. So the center of those three is supposed to be connected to chassis on that one. So is this why it's not working, or it doesn't really have any feature other than just shielding, right? I hope that is not that important for this, because it's just AC filtration and all sorts of shielding and goody stuff, right? So maybe that's not it. Yeah, but I see some transistors and capacitors and goody stuff down here. So yeah, maybe we should just see what it does, right? That's a good idea. I also really want to have a look inside the bridge. Oopsie doopsie. So this is the input. Look at that. So it's doing a little blinky here for the next 5 minutes. I put in some new cells. So when you hold this in, it's going to hammer all the way up. And then it's just going to show that it's powered on. And everything is zeroed. But look at that. If I go from 1 watt to 3 watts, ooh, it hammers negative. Except for the 1 watt range. And the other one here is doing exactly the same. So why is that happening? That can't be right. Okay, so let's do this real simple. Just take a tiny little handy here. This will do around 5 watts. And then connect it to the proper frequency range. Then the output is connected to the dummy load. So that should give us a perfect 4 watt and nothing reflected as far as I see. So we can have this in 1 watt and 1 watt. So just click this real fast. Yes, that is good. Let's go to 3 watts and then it goes negative. Yes, 10 watts. So we should expect about half, more or less, right? If this one is charged. Aha. Okay. Really? Okay, so this is still okay with the battery, and I didn't charge this for a million years. I'm actually a little bit impressed to see 5 watts, 4 watt. I mean, it really works, but it's just hammering negative. So that's actually all it does, and right now it's sucking up all the batteries because of that, right? So this is a little bit annoying. Why the heck is it doing that? And it can't be the sensors. Okay, so I got an idea. Now we'll reverse the two end connectors here, and then it's going to be reflected instead of forward, right? And we're ready to do the same test. Power is now going into the reflected, right? And that is the forward. Good. Ooh, that is weird. See, there's a problem with reflected. We should expect 10 watts. I mean, half the way here in 10 watt. Nope. Is that affected by that one? No. So let's go to 3 watt range. Okay, so the 3 watt range only tells me 1 watt. So there's definitely also a problem with the bridge in the reflected. Oh, 1 watt forward tells us it's 0.6 watts forward. Or reflected, obviously, right? Okay, reflected bridge completely murdered by something, but forward is okay. And then we got this weird. So I think we got 2 problems. I got an idea. Let's measure the DC potential of those 3. What have we got here? I'm getting deeper and deeper into this. Just can't believe this. The center point of the voltages are it just keep driving me spooky. I mean, but I really can't prove that anybody's desoldered. It would have been so easy if only I could see a little splat or something on that center point here, but I really can't prove that to be correct. I don't know, but I can definitely see somebody soldered the wires again. So, I mean, so it got to be like that. So why the heck isn't this thing working? And what is on this PCB? How do I get in there? I mean, I really need to take it completely to pieces. I didn't expect it to be that difficult. Maybe if I... Why is it always a million times more difficult? I really love designs where you can access both sides of a PCB without really getting into deep trouble. But I mean, this could have been in a connector, but it's not. Here we go. You need to remove the 2 knobs, then unscrew the front panel, and then you'll be able to access the screws for the 2 contacts. That is what holds the PCB. Well, there's actually a serial number in here. I think this is also going to be the access to remove that broken glass meter. But of course there's no need to fix that glass before we have fixed the electronics. That I think that is the order. So I managed to get the PCB all the way out. And I believe this PCB here, I wrote a little bit here about the power supply inputs, because I'm going to figure out exactly how this power supply stuff is working. But I think more or less all this board is doing is handling the power supply on off and the timing and the LED blink as well. The reason for having all those transistors, that's because it's turning on and off both the positive and the negative supply, and it's leaving the center point to the circuit, obviously. think there's a nice little reference chip down there. It's an 8589JH. And all transistors and all diodes and everything here seems to be working. So why are we having this really odd offset kind of problem? I am still circling around this center point connection. I think I just have to try and move that red wire to the center point. I think that is gotta be it. So here we go. Now I tried to put the red wire in the correct center point. This is just what I guess could be the correct center point. And look at that. Now I got a lot of weird output like that, right? And if we try the battery tester, oops, one goes one way. That can't be right. So, I mean, maybe that was right. I was having a loose connection in the batteries, and that is why it was causing a little bit of confusion. So now I got plus minus 6 volts to this system, and then I'm trying to push the battery tester. It's quite clear the positive battery tester hammers out, and the negative is not going that high. So with the center point offset 3 cells, then the battery tester's exactly the same. So unless somebody poked around with the pots for battery testing, I mean, I actually think that is the correct way it must be for some weird reason. So that means I'm a little bit back to square one here. I got the 1.2 volts on the reference chip, and I don't find anything wrong anywhere. So that is annoying. I've been poking around with this for a few more hours. Yeah. Oh, you're not going to believe what I figured out. So that voltage reference, the 8589, is a minus 1.2 volt of reference, and it is connected to the 4 highest power levels offset, and not for the first one. The first one, it is using the chip's internal offset. The op amp, the offset of this op amp is connected to the first pot right there where I wrote offset, and this is of course where you adjust to absolute 0, and that is the gain for a 1 watt readout. And then I think the idea for the negative meter like this, when I go to the higher ranges, has something to do. They're trying to add a little bit of positive biasing to the pickup diodes in the coupler, but for some reason that is not working, and there is no resistor or anything connected from the reference to that input that should, solve that negative problem here. So what if I connect that minus 1.2 volts directly to the ground? Then all this annoying negative meter is gone and is completely solved. And the funny thing is, it measures absolutely accurate and correct. So I can just remove this dumb reference and everything is perfectly fine. What the heck is that funny design? By the way, those 2 transistors, and this is the oscillator, and the reason why one capacitor is very small and the other one is 10 times as big. That is, of course, they are blinking very, very short blinks to preserve power. And this one is actually also a part of the oscillator for some reason. Yeah, so that is really weird. I can't find any other thing. There's definitely nothing wrong with this circuit, and both op amps work. I mean, this is how it's supposed to be. But I really don't like the meters to go negative like that. So I think we should kind of solve that. So that means we can stop poking around in this annoying thing, and let's look at the detector. Why was that not working in the reverse? That is absolutely fantastic. Playing around with the biasing, exactly as I said. I did, of course, remove this resistor, so where the heck is that? Here's this little resistor just to preserve power. And then I shorted the dumb reference. So now it works in forward and reverse. Look at that. Ting tang. And there's no funny zeroing problems. Oh, what kind of great things is that? So, I thought I was going to repair the coupler, but that is not necessary, since it actually works. But I want to show you how this is designed anyway. So this is the low frequency coupler, and this is the high frequency coupler. Higher, 200 to 1000, right? So, inside this coupler, there's of course a feed through inside, but there's also two pickup lines inside some Teflon, and here is one of them. So this one goes in the entire length in here, and so this copper here is just ground. So there's a resistor here at the end, a termination of the coupler element, and then there is a again a termination, but also a resistor to the diode, and that diode gives a DC voltage out. But if you look a little bit careful, you can see there's another coupler down here, all the way over here, and there's a termination in this end, and in that the other end, the same resistor, and again another diode, and this makes the other DC voltage output. So that is how it works. It is a little bit optimized for a wider frequency range, and that is of course why we have a little speed up capacitor here for the higher frequencies. We also got some resistors here that is adding a little bit of load on the higher frequencies to compensate for that, and then this is our DC. This is kind of making our DC voltage, right, on this capacitor, and then there's an inductor for that, funny enough, to ground. So that is the measurements for the lower frequency. The higher frequency one, this is more or less the same circuit, but of course you need the coupler to be a lot shorter, a lot smaller. So it is only that length, and they are now on the same line, right? So again, there is a termination resistor to that end, termination resistor to that end, and then we pick up here in the middle in the two directions, again with resistor, variable, trimmers and all that kind of stuff, and then we go to DC, and here's a little disc capacitor and a resistor. So the two forward and reverse DC signals just go to a switch, and you can select what if you want this or that, and then it goes to the cable, and the cable goes to the readout unit. So that is how it works, and it's really, really beautiful. Oh yeah, by the way, a classic thing with a dummy load like this, to make the dummy load work at a higher frequency at using a lower cost component. So down here we have the resistor. They're actually adding a trimmer capacitor directly on the input to the chassis, and that is just to give a little bit better match, and this will remove some of the inductance there is in the load. So yeah, that is kind of nulling that component away. I don't know, we can't really see the load because it's behind this piece of brass. It's holding it down to the heatsink down here. It's actually quite impressive. You can do 30 watts continuously, but 100 watts for 3 minutes. So that is a very useful kind of load here. So I think that is all I wanted to show you guys. Have fun and see you tomorrow. Bye bye.